In this video, we want to introduce our reinforced concrete section. And we're going to start by talking about reinforcement and general concrete principles. And then we'll finish up this video by talking about reinforcement related to bending stress. I've got three quick slides I want to go through. The first slide right here talks about cover. And I know you take a reinforced concrete class, so I don't want to get into a lot of details here, but there's just two or three major things that I want to cover quickly that sort of overlap with that class, but are general concepts to consider as far as concrete construction and design is concerned. The first one is actually to do with cover. That is how much concrete has to overlay the reinforcement along the edge. And it's a function of both whether you're using formwork or pouring up against the ground, and also then what type of structural element you're constructing. And so for walls and slabs, generally we would think of using about 3/4 inches of cover. Again, that's 3/4 inches of concrete on the exterior side of the reinforcement. And for beams and columns, because these are a little bit more critical as far as the elements are concerned, we would bump that up to about 1.5 inches of cover. It also has to do with the size of the rebar that's typically contained in those structural elements. For walls and slabs, it's often smaller rebar. And those tend to be thin anyway, 4 to 6 inches, perhaps maybe a little thicker if it's a big heavy-duty reinforcement slab. But beams and columns tend to be on the order of 10 to 12, 16, 18 inches, and perhaps even bigger depending on the type of structure. And so 1.5 inches of cover minimum for those. Anytime that you're pouring reinforced concrete against something that's touching soil, for example, a footing, we bump that minimum cover up to about 3 inches. This next diagram down here has the general geometric properties for reinforcing bars. And you can see on this side over here, we've got number 3 bar, 4 bar, 5 bar, etc. I'm not too stressed over the weight. That does factor into the design a little bit, but we won't deal too much with it in this class. It also affects the cost, and you would want to keep track of that as well. If you knew how many bars you'd have, you also need to keep track of how much weight it was, so you could do your estimate correctly. For the sake of what we want to talk about real quickly, if I had a number 4 bar, what would be the diameter of that bar? Up until you get to the number 8 sized bars, it's really easy because it's simply the number of the bar divided by 8. And so for a number 4 bar, the diameter would be 4/8 of an inch, or you can reduce that down to 1/2, and you can see that there. You could also calculate the corresponding cross-sectional area doing pi r squared or pi d squared divided by 4. Those are the two equations to get the area. Or you can simply jump in here and grab the area of the cross-sectional area of that piece of steel. That would be in square inches. Again, the cross-sectional area of a number 4 bar. So this table becomes really handy for quickly utilizing the diameter and the cross-sectional area as a reference. Note that when you get to bars that are bigger than number 8, the rule of dividing by 8 generally holds true, but isn't as exact anymore. And so you'd want to come in here and look up the actual diameter for, didn't mean to cross that out. You'd want to come in here and look up the diameter for any bars that you're dealing with. All right, this slide wants to talk really quickly about compressive strength. I know you deal with this in in your concrete class. Generally speaking, when you're dealing with structures and you're dealing with concrete, concrete cylinders is the way to go. And it's pretty standard just to take some samples, create some cylinders right there on the job site, take them back to a lab, cure them for however many days you're testing. 28 days is sort of the standard in the industry that's written in the specs. But sometimes you'll test one earlier, 7 days or 14 days, and see where your strength is early on. Number one, that's a good indicator of whether you're going to make it to the full strength in time. And number two, if you reach strength sooner than later, then oftentimes you can move forward with other elements, especially if you're pouring something that's got to be holding up some other portion of the structure. For instance, columns that you're adding other additional floors above in a big commercial building or something like that. Another thing that sometimes is done is what we call a maturity curve. We see this a lot of times with bridge decks, where we want to know the true strength of the concrete as it's curing. And essentially, we know that based on this curve right here, if I plotted compressive strength on the y-axis and plotted that relative to time on the x-axis, what we would do is we would develop some sort of an area under the curve. And there's correlations that exist that say it's going to take a certain amount of area to reach a certain strength. And so we know that compressive strength is also going to be a function of temperature and moisture and some things like that. Let's say you pour a bridge deck in cooler temperatures, it's going to take longer for that compressive strength to build up. And so eventually you'll hit the top of the curve. That curve shouldn't be quite so straight line. Actually, let's redraw that. So you'll reach the same amount of strength, but notice that, I'm going to make a number up here, it may take additional time for it to reach the same area. And we know that what they're able to do is keep track of the area under the curve by plotting the compressive strength versus the time. And or rather, they're able to correlate compressive strength with time. They keep track of the time, and therefore they, based on the temperature and other conditions, external conditions, they're able to correlate with what the compressive strength would be. One quick thing to note on this slide right here: standard compressive strength for concrete will vary from about 3,000 psi to about 5,000 psi. Frankly, 3,000 is just a little bit low for structures. 3,500 is fairly common. At the DOT, 4,000 was kind of the standard that we used. 5,000 is starting to push some higher strength concretes. But the point is this: these are in the ballparks of what to expect for compressive strength. The final figure that I want to show here has a lot of extra stuff in it that we don't necessarily need. But I wanted to just quickly give you a table that gives you an idea of how much reinforcing steel you would need for bending stress, since that's kind of the topic of this one right here. And we'll split the table in half. The top half is for this yield strength right here. This is for our steel. That's the reinforcing steel, the rebar that goes in the concrete. Generally two different strengths that are utilized. For structural steel I-beams, wide flange sections, it's common to have 36 KSI and 50 KSI steel. For rebar, we often deal with 40 KSI steel or 60 KSI steel, and that's how this diagram is split in half. And then you'll also note that it also has the compressive strength of the concrete. So that's the F prime C. And we've got 2 KSI, 3 KSI, 4 KSI, or 5 KSI. If you had something in the middle, you could interpolate. Again, 2 is really low. 3, 4, and 5 are a little more standard. We'll go ahead and use 4 for the sake of this example right here. And you can just ignore the metric column because we're dealing with the English units. The next piece that I want you to pay attention to is not this latter stuff, slightly beyond the scope of this class, but this P right here represents the percentage of rebar that you would need. And this is kind of a minimum percentage of rebar for what they call a balanced section. And so using 40 KSI rebar with 4 KSI concrete, we would need to have a cross-sectional area. If my cross-sectional area of my beam looked like this, and we threw in 2 pieces of rebar right here, the percentage of rebar relative to the total area of the beam would need to be 5.82%. Whoops. And that's what that number means in that chart. So again, this gets you a balanced section for percentage of steel needed in the cross-sectional area of the beam.